So now we're going to tackle Stokes' theorem, or Stokes' theorem. Okay, so again, like in Green's theorem, we're going to have a relation between a line integral. So in this case, it's the line integral over the boundary of S. So line integral is denoted by f dot t, and then ds. So this line integral, Stokes' theorem says, Stokes with an apostrophe, that this is equal to the double integral over S itself, the surface, of the curl of f dotted with the normal vector, ds, d big S. Okay. There's a difference here, but the important part is that you're dotting it with the normal vector. So this, as I said, this is the line integral over the boundary of S. Oh, so over boundary of S. And this is, as you can see, the double integral. So, well, this is the, I'll just call it the surface integral because it's over a surface, right? So surface integral of, and what this signifies is the normal component of of f, of curl of f. Okay? So, there is a special case. Special case. And I noted this on the second slide, I believe, of this video when I was drawing the three different examples of surfaces. Three different examples of surfaces, not the three different, but because of course there are many more. But a special case is if the surface is closed, this means that you have an empty boundary. Remember how we had the potato-looking thing? So empty boundary of S, and then the surface integral. Which is this thing, right? So the curl of f dot n ds is going to equal 0, okay? Because there's nothing going through, really. Okay, so that's basically the statement of Stokes' theorem. It's, as I said before, it's a generalization of Green's theorem, so it looks very similar to it. You kind of just replace the d's, we replaced the d's for domain with s's, which stand for surface now. And now we have the normal component over here, and this part is different. Okay? Alright, so now we have another instance, I guess, or a case where f, our vector field, equals the curl of some other vector field. And I'll just call that capital A arrow. So what A is called is the vector potential for f. Okay? And what this means, what this signifies, is that if we apply Stokes' theorem and we do we take the line integral over some curve, and then we dot A with t. So we're taking the line integral of A, okay? So something like this, and then what Stokes' theorem says is that it's equal to the double integral, or the surface integral over S of the curl of A dotted with the normal vector, and then d big S. But as you can see here, the curl of A is actually equal to f, right? Because this is our first condition here. So that's going to be equal to f dot n. So it'll look something like this. So the double integral over S of f dot n, and then ds. Okay? So let's draw a picture of what this looks like. So let's say we have a surface. It goes out like this, and it closes in a circle here at the bottom. This is the curve, right? This is its boundary curve. So let's say this is C, right? Let's call this C. Okay, that's the circle down there, and this is S. I'm going to call this one S1, S sub 1. Okay, so specifically this is S sub 1, all right? And now, let's see what would happen if we did the same thing, but now let's connect another surface, a separate surface, to this circle here. So S sub 2, this is a different surface entirely. This has the same boundary curve as S sub 1. So if we took the line integral over C again, and we would get A dot T ds, then that, by Stokes' theorem, would equal the integral over the surface. So now we're concerned with S sub 2. So we can put S sub 2 here, and then compute curl of A, which is equal to F, right, dot N ds. So since these are equal, these two line integrals are equal, then that means that what they equal respectively must be equal as well. So these must be equal, which is an important finding because this means that the surface integral, so I'll write it down, the surface integral of a vector field of a, I'll just write this, so of a vector field F with vector potential, as I've defined here, A, with vector potential A is what is called surface independent. Surface independent. Okay, I was going to abbreviate. Independent. So what this signifies is that whenever you have some vector field F up here, okay, and if it has the same, if it has this relation that it is the curl of another vector field, so this is the important condition that you have to begin with for something like this to actually be true. So if it is the curl of another vector field, then you do have this relation here that any line integral that you take is going to be equivalent to the surface integral, and then the surface that the boundary curve is connected to, this boundary curve down here, that doesn't matter. Okay, so basically you could draw any surface, and just as long as it comes back to this boundary curve, then your line integral and your surface integral are going to be the same. Okay? Alright, and then another important term that you might see, and we've seen it before in line integrals, I believe. Anyways, we've calculated the flux before, and what the flux is flux of F, I guess you could say. So of some vector field, flux of some vector field through a surface S is equal to basically the surface integral, and what I'm writing now is tying it back to the previous slide when we had, okay, I'll get rid of that for now. But anyway, so what we had on the previous slide was the double integral, or the surface integral, of the curl of A dotted with the normal vector d capital S. And this was equal to, this is just F, right, our special condition. So we have the double integral over S of F dot N ds. Okay, so the flux is equivalent to this. All right, it's the surface integral, basically, of the normal component of something going through the surface. Okay, that's the definition of flux. And what we found on the previous slide about about the surface integral, or the line integral of the boundary over the boundary being surface independent, means that it depends, the flux then, the flux, which is this thing, so flux through surface S, depends only on the oriented boundary. Okay, so on the oriented just means that direction matters, remember. So on the oriented boundary, which is denoted funny symbol NS, and not, and this is the important part, and not on the surface itself. On the surface itself. So again, this is kind of a more formal definition of what surface independent means. Okay? So basically, yeah. So that's pretty much it. And now we'll do an example of finding the surface integral.
And wet fishes picked up by